Okay, so we've been talking about the electromagnetic spectrum and waves and things like that, and we're going to kind of focus in right now on the part of the electromagnetic spectrum that we can actually see. So this week we will be talking about light. Waves, don't forget about the red slides. This is when you should take notes. You should have your waves handout. Don't forget to look for the owl and describe them at the end, and give me a 2 to 3 sentence summary of what you learned. All right, so here's a question for you. What exactly is light? This is a little bit of a tough question to answer. I know it's one of those kind of you know it when you see it, you know when the lights are turned on and when they're off, but what is it? I mean, is it stuff? If you turn on a light and put your hands out, can you fill up your hands with light and does it get heavier? Are they little particles like what you're made out of and what stuff around you is made out of? Would you even call it stuff? Um, a little hard to say, and this is actually something that scientists have struggled with for a long time. And um, from several experiments that we'll talk about in class, um, this is actually a very hard question to answer. What we've found is that light is really kind of one of the strangest things to figure out, and there's a lot of very odd things about it. And we'll talk more about that in class, but I want to give you some of the basics, a kind of starting point. So the big question has always been, is light a wave or is it a particle? So we understand this idea of waves, and we understand that if you make a wave in the water, we've talked about this idea that the water is moving, but the wave is kind of maybe something different from the water. We talked about this idea of like transverse waves and how the stuff of the wave moves and how the energy of the wave moves. So in water, the when you make a wave, the actual water itself just kind of goes up and down, but the wave seems to move across the surface of the water. So the wave is in some ways different from the water itself. The particles of the water and the wave are two different things. And so we can think of something as a wave, um, but then we could also think of it as particles. And so light has been discussed as being particles that are called photons. You might have heard of protons and electrons and neutrons and things like that. Well, a particle of light has been described as a photon. And for a long time, people thought that light was made of little particles. Like the light from the sun was actually like, think of it like little golf balls or something like that being shot out at us from the sun and kind of landing on the earth. Uh, um, this is an interesting shot here. If you take a camera, a digital camera, the way that a digital camera works when you take a picture is that it has little pixels on the screen. And if light hits one of those little pixels, one of those little sensors, then that sensor sends an electronic signal to the brains of the camera. So here's what happens. You can see these three images here, and if we take a picture of a light source, and the first picture is sort of just the normal light, and we see that that's kind of a light source there. And if we make that light source a little bit dimmer, what we start to get is kind of this graininess. And if we make it really, really dim, then what we see is that there are individual little bits of light that are hitting different spots on the camera. It's not like a constant flow of light. It's more like individual little pieces of things. So think of this as like a stream of bullets instead of like a stream of water. And that's a little bit of a weird analogy there because both of those things are particles. But when we think of bullets, we think of several individual things. When we think of water, we think of this continuous ongoing thing. And what we see from these pictures and many other bits of evidence is that in fact light is more like bullets, that it's more like a bunch of little bits of things that are kind of flying at you. So when you turn the light on, it's sort of like shooting a bunch of little bullets out, but they're so small that we can't see them. So that was one way of thinking of it, that light is a particle, and we have quite a bit of evidence that shows us that this is the correct way of thinking of it. But then there's this experiment. Okay, so all right, if if this is true that light is made up of little particles, like little bullets, well, what happens if we have this wall here that has openings in it, has a couple of little doorways. It has a doorway there and a doorway there, and we start shooting all this light through it. Well, if light is made up of these little things, let's think of it again like we're shooting little bullets at this wall. So what would we expect to see in this experiment? You can see it up here too in sort of more of a 3D kind of thing. So we're shooting all of this stuff, all of this light that supposedly is made of particles, and we shoot it at this wall. What do we expect to see? Well, okay, so this little particle here is going to hit off this wall and go off that way somewhere, and this particle here is going to go off that way somewhere, bounce off the wall. All of these guys are going to bounce off this wall and go that way and stuff like that. But these guys here are going to get through, right? So these guys are going to get through and they're going to hit the wall back here, and these guys are going to get through and hit the wall back here. So we would expect to see some little spots of light right here and a little area of light right here, and kind of darkness in this area and darkness over here and darkness over here. We would expect to see two little slits of light, right? A little line of light there and a little line of light there. So that's what we would expect, and I think you would agree that that's what you would expect if you were, say, if these were bullets, or if these were balls that you were throwing at this wall or something like that. That's basically what you would expect to see. So we would expect to see something kind of like that, a pattern along those lines where you would see light in this area, and basically what we're doing is this is like what you would see if you were looking at the wall here, okay? So we would see light in that area, and we would see light in that area, and we would see darkness everywhere else. In other words, we would see light where the light gets through the little walls, and we wouldn't see light where it's blocked. Well, that's not what we see. And here's where science is key and where science gets really interesting. When we have a hypothesis about something and we think something's going to happen a certain way and it doesn't happen that way, well, that's kind of what science is all about. That's when we're really figuring things out. So here's what happened in this experiment. This experiment is called the double slit experiment because of these two slits here, these two openings in this wall. And so what happens is they shine the light through here, and what they get is a pattern that looks like this: light, 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 and light, and darkness in between, like what you see over here. This is an actual picture of what you see when you shine light through two very small openings. By the way, this animation, this drawing of this is really not the right sizes. These slits are really, really tiny in the actual experiment, and they're really close together. And we'll actually do this double slit experiment in class, and I'll actually show you this in class. But this kind of reveals some of the weirdness of light. So what does this tell us? Well, if you have been following along in class, this should look like something to you. And the scientists that saw this, well, fortunately, they were following along when they took their classes, and they recognized this as a certain type of pattern. So you guys may remember talking about this idea of waves and the idea of wave interference. You can see it happening in water up here. You can see another shot of it over here, and you can see this idea that in some places the waves kind of add to each other, like right there. And in some places, the waves tend to kind of cancel each other out, like we don't have really much of a wave in that area. So this is called constructive and destructive interference. You may remember this. If the crests line up with the crests and the troughs line up with the troughs, we get constructive interference, and it makes the wave bigger. And if the crests line up with troughs and troughs line up with crests, then we get a destructive pattern, and they destroy each other. Well, we can see that happening in this image here. In this area, there are waves here, But in this area right here, kind of try to circle it for you, you can see that there are no waves there, right? And we see that happening here and here and here, where the waves, destructive interference between these waves happening in all these little spots that I'm highlighting here, right? And so if we looked at this and we kind of marked on a wall here where there are waves and where there aren't waves, we would see waves here, here, but no waves in between these lines that I'm drawing, right? Waves, waves, but no waves in these areas in between. Now, if these are two light sources, like if we had a wall here with two openings in it, an opening here and an opening here, just like our double slit experiment, this would be like two sources of light coming through, right? And so what we see is a pattern like this red part that you see below down here. We see an area where you have light, no light, light, no light, light, no light, just like these patterns of waves. And so scientists recognize this as a wave interference pattern. But I thought light was particles, not waves. Well, that's where the problem is here, and that's why light is so difficult to describe and is so tricky, because basically light is both particles and waves. And this is very strange. We'll talk about this more in class, but this is a really weird thing to try to figure out, and it's very confusing to scientists, and basically they've had to settle on the idea that it's kind of both at the same time. It is both, if we go back to the analogy of a water wave, it is both the water and the wave going through the water at the same time. So we'll talk more about this in class, but that's the double slit experiment, and it is an extremely famous experiment in science, and something that shows us that, I think in a general way, at least shows us that the world, the universe around us is something that we don't quite fully understand, and there's a lot of things about it that are very strange to us. All right, so we'll go over that more in class, but that's kind of an interesting idea. So that double slit experiment showed us that light is actually behaves, at least in some experiments, behaves as a wave, and in other experiments it behaves as a particle. So this brings us to our definition of what light is. Light is a particle known as a photon and also a wave, and it goes out in a straight line unless it bumps into something. In your notes, you should be able to answer this question: what was that famous experiment that we were just talking about that demonstrate that light is a wave? Now, let's talk about this idea of light bumping into things. You know about this. You know about light sort of bumping into a mirror, or light going through water, or things like that. This is definitely something that you are familiar with. So let's start off with some simple stuff here. The objects that light can bump into can come in three varieties. They can be transparent, which means all of the light goes through them. They can be translucent, which is kind of in between. Some of the light goes through, but some of it doesn't. And they can be opaque, meaning that no light goes through them. You cannot see through them at all. So let's talk about this idea of bending light. This is a great picture right here. Check it out. It looks like the girl's head is kind of cut off here. But you guys have probably seen something like this before, and you could probably guess that this is kind of not exactly a trick, but it's not, but obviously the girl's head isn't really cut off. And you could probably figure out that maybe it has something to do with this water here, right? And you've probably seen this before, where maybe if you're in a pool and you look down at your legs and they look all kind of wobbly, or if you have a straw in a glass of water and it looks kind of bent. So you've seen this before. So, okay, first of all, you're going to see at this point this part of your notes where it says video questions and check for understanding in those boxes there. We're going to do that in class, so you don't have to worry about filling any of that stuff in right now. All right, bending light. First of all, let's talk about reflection. Reflection is when light bounces off of something, when it hits something and bounces off of it. Now, I want you to think about this. I want you to look around at the room that you're in right now, and it probably doesn't look much like this room, but look around at the room, and I want you to look for things that are reflecting light. And so you might look at something like, okay, like this table here, right? We can see the reflection of those pillows in the table, right? And maybe even like a shiny piece of metal or something like that, like what's on this computer. We can see that reflecting light. But is that the only thing that's reflecting light? Well, let me ask you this. How are you seeing all the colors in this painting? How is that light getting to your eyes? Or if you're looking around in your room right now, how are you seeing the colors on the walls? Doesn't light have to hit you in the eye in order for you to see it? We kind of talked about this a little bit before in a previous video. So in order for you to see this stuff, there's got to be a light somewhere, right? There's a light source in this room, and the light is coming from that light source, bouncing off of this and hitting you in the eye. So this is also an example of reflection here. In fact, everything around you that you see is an example of reflection, but you would probably agree with me that this type of reflection here is kind of different from this type of reflection here. And that's what scientists say too. There are two different types of reflection. So the first one, and the more common one, the actually more normal one, even though you don't usually think of it this way probably, is what's called diffuse reflection. And this is when light beams are reflected in many different directions. And as you can see from this picture here and this picture here, which would be kind of like a magnified version of this picture on the left, that usually happens when you have a rough surface. And you can see, as we said before, light travels in straight lines, right? So it comes in here. But because this is a rough surface, this light bounces off this way, and this light kind of bounces off that way, and they go all over the place in all different directions. You can see this shown in this drawing of a sphere here, right? You might not think of this as reflection, but light has to hit this and bounce off of it in order for you to see it. So that is an example of diffuse reflection, and this generally happens with things that are not really super smooth, okay? Which is almost everything around you, okay? So the other type of reflection that you can see here is called regular reflection, and this is the kind of reflection that you're more used to, the kind of reflection that we think of in shiny objects and mirrors and stuff like that, where you can see yourself in them. We'll talk about this guy a little bit more, but this is a drawing by a guy named M.C. Escher, which is one of my favorite artists. And you can see in this picture the idea that with a smooth surface, all of the lines of light kind of reflect off and go off in the same direction. That's why everything looks the same when you see it in a reflection, because the way that the light is going in is the same way that the light is going out and hitting you in the eye. All right, so we're talking about mirrors here. So the first type of mirror that we need to talk about when we talk about plane reflection, regular reflection, is a plane mirror. And that's like the regular kind of mirror. And when they use this word plane here, they mean like a geometric plane, like a flat surface. But you can think of it as in the word normal or regular, okay? But this is just a regular flat mirror. Now, when this happens, we have something called the law of reflection. And the law of reflection is that the angle of reflection equals the angle of incidence. And I just said a bunch of sciencey words that you don't know yet. But basically what that means is that if you have a light beam going in, the angle right here, or an angle between sort of, if we draw a perpendicular line, like a straight line, a line that is perpendicular to the surface of the mirror, this angle here and this angle here will always be equal to each other. So angle A, we could say, is equal to angle B. Now you're going to have to get used to drawing this. So take a look at this little animation over here. You have to be able to draw it like this, all right? You have to be able to draw the line coming in and the line going out, and draw a little kind of arch like this showing that angle, and understand that these two angles are equal, okay? So let's try this out. So you should be able to see this in your notes, and let's start filling these things in so you know what these words mean. So this is the incident ray, and by the way, notice that the arrow is going out this way. So in this picture, the light is coming in from this side, I have been showing you the light coming in from the other side, but it doesn't matter which side it comes in from. In this case, it's coming in from this side and going out that side. All right, so this is called the incident ray, the beam of light that is coming in. Picture a flashlight over here, okay? Flashlight's over here, shining the light down this way. So the beam of light that is going towards the mirror is called the incident ray. The beam of light that is going away from the mirror is called the reflected ray. That one should be pretty easy. This imaginary line that we draw that is, see this little box right here, that means a right angle, right? You should know that. And that means that line right there, which is perpendicular or right angle to the mirror surface, is what we call the normal. So these words up here now should make sense. This is now the angle of incidence because it's between the normal and the incident ray. And this guy over here is called the angle of reflection because it's between the normal and the reflected ray. So make sure you are good at drawing this kind of stuff. Do a really good drawing here. Well, the drawing's already there for you, but make sure you label these and make sure that you can do these kind of drawings because you will be tested on this. All right, now we talked about flat mirrors, plain mirrors, but there are also curved mirrors like a spoon or the mirrors at a fun house or something like that. And I would suggest that you try this out. If you can, pause the video right now and go grab yourself a spoon that you can see yourself in. And I want you to kind of try this out. Okay, are you back now? Okay, good. All right, so we have concave mirrors and convex mirrors. So a concave mirror, when the light comes in, it's going to get reflected at an angle, and this all follows this idea of the law of reflection that we just talked about. Because the mirror is curved, it's going to send these guys down this way, and anything coming in down here, it's going to kind of send up this way. And some key things to notice about this is that they cross over right there, and then the stuff that was down here is now up here, and the stuff that was up here is now down here. And last time I checked, when you have something that was on top is now on the bottom, and the thing that's on the bottom is now on top, we usually call that upside down, right? Okay, so that's a good way to remember it. Concave goes in like a cave, so try to remember that. So we'll do a little activity with this in class, but for right now we can just kind of draw some lines here. Please make sure that you draw these lines very, very accurately. These need to be exactly right, exactly the way that I put them in here, okay? So here are your incident beams, the rays of light coming in. There's a reflected beam going down, and there's a reflected beam going up. And as I said, that makes the thing that was on the top on the bottom, and the thing that was on the bottom is now on the top. So that's upside down, all right? And right there, that point where they cross over is called the focal point. If you got your spoon, try this out. Hold the spoon close to you and start to pull it away from you with where you're facing the concave side of the spoon, the side that you would eat off of, okay? And take a look at what happens and see if you can maybe tell me in class what happens. This is the Hubble telescope. You may have heard of this. This is the mirror in the Hubble telescope that collects all the light. And you can see that one thing about this is that this is a concave mirror and it creates a very magnified image of this person. Now, that person is standing inside the focal point right now, and we'll talk about what would happen if he stepped back outside of the focal point and what it would look like in there then. But again, like I said, try that out at home with a spoon. There it is. That should be kind of what you look like, and what you'll notice is that the person is upside down there. So concave mirrors create an upside down image, at least when you are past the focal point. If you're inside the focal point, then it creates a magnified image. Convex mirrors, on the other hand, well, the light comes in and they spread apart. They go away from each other. This is called diverging. Okay, so they go away from each other. And so notice that there is no focal point here. They never cross over each other. And they never, so what happens is the stuff that's on top stays on top and the stuff that's on the bottom stays on the bottom. So we will not get an upside down image from this, and there is no focal point with this. Okay, So here we go. Draw your incident rays, and there's your reflected rays going away from each other. And so that's kind of the idea of how that works. So we could also think of this as like incident rays coming in here and bouncing off and going to your eyes like that. And notice again that they do not cross over each other. So here you see our concave side of our spoon and our convex side of our spoon. And you can see that the concave side shows the picture upside down, and the convex side shows the picture right side up, because the beams of light do not cross over with a convex mirror. So those are the basic things that you need to know about our first topic on light. Light is both a particle and a wave, and we'll talk more about the weirdness of that in class. We talked about objects that light bumps into and that they can be transparent or see-through, translucent, which is kind of sort of see-through, and opaque, which is not see-through at all. We talked about reflection and diffuse reflection, which is all the colors and things that you see around you, and regular reflection, which is kind of what you usually think of when you think of reflection, and that's mirrors and shiny objects. And speaking of mirrors, we talked about plane mirrors, and plane mirrors and the law of reflection. Plane mirrors are flat mirrors, and remember, the law of reflection means that the angle of incidence equals the angle of reflection. We talked about concave mirrors that give you a magnified image if you're up close, or an upside down image if you're further away. And we talked about convex mirrors like the ones that you see on a school bus or in stores sometimes, and those give you a very wide image so you can see a lot of stuff. We'll talk a lot more about this in class, and we'll do a whole lot of experiments with light, and I will see you then.